Hey everybody, welcome back to Young Engineers of Today. I hope you had a good weekend, and I hope you're ready to continue with OpenRocket because that's what we're going to be doing today. I saw your rocket, by the way, Mateo. That was pretty awesome. I like that. It was a pretty well designed one, so nice work. Um, so you already know all this anyway, but if you want to follow along, you're more than welcome to. I don't know. I'm probably not going to be going over anything that you don't already know, but just so you know. But anyway, for those of you who are not familiar with OpenRocket, well, I'm here to enlighten you on thrust curves and uh, graphs and things of that nature. That'll all be made clear later. Anyway, I'm going to go ahead and get OpenRocket opened. So just as a recap of the UI from the last time around, over here we've got our tree of rocket parts. It lists everything, including stages and parts and subparts and things like that. And the tree design makes it easy for you to be able to drag and drop new things. We can add new stages and, call them different things. But we're going to keep it on the sustainer stage because that's just like the basic stage. And one stage rockets are going to have that sustainer stage. That's fine. We'll keep it as is. We've got our add new components block over here, which allows us to, well, add new components. As you can see, a lot of them are grayed out because they need a part to be attached to. We can't attach fins to nothing. We can't attach, parachutes to nothing. So we got to have something like, for instance, a body tube, which allows us to then subsequently attach fins. And then we can attach a bulkhead, and we can attach a streamer, and we can attach a shock cord, and we can attach a coupler, and, just all kinds of different stuff. If we delete the body tube, we delete all that other stuff because it needs to be attached to something. So that's what that add component area is for. That's where we can add all of our components for a rocket. Now keep in mind this stuff all happens in order too. So if we add the body tube and we add the nose cone, as you can see, this kind of freaks out because the body tube is super duper thin right now because we added the body tube first, and we can check up here in our rocket design. Easy to fix though. All we have to do is just make sure our nose cone is listed before our body tube, and then everything works just splendidly. So let me go ahead and delete those. Which brings me down to the third thing, which, I sort of brought up looking at down here, and I'm sure you guys noticed, this is our rocket visualization area, fancy term. But basically, it's just where we can see our rocket as it's being built with a number of different views. We've got a side view, we've got a back view, then we've got 3D views, which allow us to sort of look at the kind of like what our rocket would look like if in real life, sort of, kind of like it gives us an idea of what our rocket might look like so that we can do more than just sort of imagining what a rocket's going to look like with all this stuff. So if we did something like this and then we went to, 3D finished, 3D on what? What happened? Why is it not? Well, it should be there. There we go. I just need to click on stage one. So as you can see, like they put like a texture on the body tube so they look like cardboard and things like that, and a texture on the fins so they look like cardboard or balsa wood or something. So you get a better idea of what your rocket might look like if you were to build something like this yourself. And we'll go back to the side view. A few other things to take note of here in the rocket view. We've got the name of our rocket, obviously, the dimensions of it, so the length of it, the diameter of it, the mass. We've got this little thing down here, apogee, max velocity, max acceleration, which gives us an idea of the maximum height the rocket will reach, which is apogee, the maximum speed the rocket will move, which is max velocity, and the highest rate at which the rocket will gain speed, which is the max acceleration. All pretty self-explanatory stuff, except for maybe the term apogee, but, Now you know it. Apogee is just simply the highest point in the rocket's flight. So we got all that. Then we go over here, we've got stability and CG and CP. So what exactly are those? Well, we've got two circles here, right? We've got a circle broken up into quarters with some blue quarters and some white quarters. And we've got a red circle. The blue circle represents the center of gravity or the center of mass, whereas the red circle represents the center of pressure. These both are well, they're two separate things. The center of gravity is also known as the center of mass, essentially, because it is you can think of it as the midpoint between the distribution of the distribution of weight on an object. So in essence, you're going to have you're going to have an equal amount of weight on one side of the center of mass versus the other side. Essentially, it's the midpoint weight-wise. Not necessarily the midpoint, length-wise or anything like that. That's a totally different thing, because you can have, like the nose cone can be heavier than the rest of the rest of the rocket, so your center of mass is going to move closer to the nose cone, or your center of gravity. Another interesting thing to note is if you throw objects and allow them to sort of spin an arc, objects will spin about their center of gravity or center of mass. So as you can see, the center of gravity here on this hammer is right about the head. So it will spin about the center of gravity as the center of gravity itself traces an arc through the air. So if we were to throw this rocket and make it spin, and there was enough weight so that it did it reliably, the rocket would spin about its center of gravity, and the arc that it traced would be traced using its center of gravity. Now, the center of pressure is the point at which the pivot point at which the rocket, the pivot point at where the apparently I'm tongue-tied today. It is the pivot point on the rocket created by the forces acting on it from things like drag and aerodynamics and stuff like that. So you're talking about the air resistance from the nose cone and the air resistance from the fins and things like that, trying to correct the rocket's path. They will pivot about the center of pressure. So now these two are basically in direct competition for one another. The rocket is trying to pivot about its center of gravity due to its weight, but it's also trying to pivot about its center of pressure due to the fins and the nose cone and stuff like that. So we have to keep track of both of those, because both of those work together in order to create a stable rocket. In essence, they can kind of work against each other and cancel each other out so that we have a stable rocket. So for that reason, we use them in order to determine stability of a rocket. And we've also been able to sort of figure out a general rule of thumb. This doesn't apply to everything, but it applies in many situations. You want a rocket that has a center of pressure that is about 1 to 2 calibers behind the center of gravity, somewhere in that range, generally speaking. Not all the time, but generally speaking. Now, what's a caliber, you might be asking? Well, a caliber is simply the diameter of the rocket at its thickest points. So if we go back to the side view, as you can see, obviously the center of gravity is on the wrong side. If we wanted to actually use this line to measure something, we would want the center of gravity to be about here and the center of pressure to be sort of in this general area, because it's somewhere between 1 and 2 calibers. As we can see, the program is kind enough to calculate that kind of stuff for us. It gives us the center of gravity and the center of pressure relative to the front of the rocket, so their distances from the front of the rocket, and then it gives us a stability in calibers. In this case, this is 0.442 calibers, which is not quite enough in order to keep the rocket stable. We would want a slightly higher stability, or excuse me, yeah, we would want a slightly higher stability value, like slightly more caliber, but not too much. But yeah, so that is very basics. Now what we're going to do is we're going to go ahead and open up an example. If we go to File and then Open Example, we can see a simple model rocket. We've got here design name, a simple model rocket, designer, Sampo Niskanen, whatever. Anyway, and then we've got a very simple rocket design down here. Now the important thing to note is that this is the bare minimum for a rocket, essentially. It's got a nose cone, necessary for aerodynamics. It's got a body tube, necessary to hold all the stuff that the rocket needs in order to fly. It's got fins, necessary for stability. It's got a launch lug, necessary for stability on launch. It's got a motor, necessary for it to do rockety stuff, like motor around. It's got a motor mount, which is necessary to keep the motor in the rocket. It's some centering rings, which are good. We'll explain what centering rings are in a minute. It's got some recovery wadding, pretty necessary in order to protect the recovery system from the ejection charge. It's got a shock cord, which is necessary to keep the nose cone connected to the body tube. And it's got a parachute. Well, a recovery system, which is necessary in order to recover the rocket. Now, that's the thing. I mean, like, it doesn't have to always be a parachute, which, by the way, that's what this little dotted line diagram represents. It represents a parachute. Because it's easier to do that than just to have try and like have a picture of a parachute in there. You can see it in the 3D unfinished. There's the parachute representation, but again, this gets a little bit difficult to read because that's the shock cable or the shock cord, and that's the recovery wadding, but they have the exact same texture on them. So you might be looking at this going like, okay, so is that just a really weird shock cord? Like, what is that? But anyway, so that for that reason they have actual symbols which denote them. This is just a generic thing representing the wadding, and then this right here specifically represents the shock cord. It's got the sine wave going on, or maybe it's a cosine wave. But anyway, we'll go ahead and zoom to fit, which is at 100%, and we're looking at a very basic and simple rocket design. Now, as you can see, it's got a motor already mounted in it. I believe, yeah, it's a C65, so it's a pretty big motor. So we got an apogee of 314 meters, a max velocity of 94.8 meters per second, or Mach 2 or 0.28. So it's going almost a third the speed of sound. That's what Mach represents. If you're going Mach 1, you're going exactly the speed of sound, which is what, like 700 and something miles an hour, 725 miles an hour or something. Max acceleration is 183 meters a second. Mach 2.55, that's right. I think I remember that. And it goes up to like 1,000 meters or something like that, doesn't it? Or at least in the screenshot you sent me. I believe, maybe, if I remember correctly. I might be misremembering it. Anyway. Oh, your new one. Oh, wow. Okay, so it goes almost 3,000 meters high. Also, for those of you who are trying to convert that to, Murica units, a meter is roughly 3 feet. Roughly, it's 3 feet plus some change. It's like 3.5 feet. So if you want a very rough estimate of how high something's going to go, 314 meters at this point is going to be about 1,000 feet up in the air. 3.3 feet. Okay, yeah. So 3 1/3. So it's yeah, about 1,000 feet in the air. 2,684 meters. That's going to be, oh, let's see here. 5, 7.5, 7.7. It's going to be almost 8,000 feet. It's going to go up almost 8,000 feet. And it's going 2.55 times the speed of sound if it's going Mach 2.55. Max acceleration is the fastest at which it is going faster. So as you can see in this example here, it's going 183, its max acceleration is 183 meters per second squared, which means that this rocket does not spend very long under max acceleration. like at all, because its max velocity is 94.8 meters a second, which is less than its max acceleration. If it's going 183 meters a second squared for an entire second, it will be going 183 meters a second at the end of that second. It is not. It is going about half that speed, which means that it spends at the very most, it spends half a second under max acceleration. Realistically, it's probably spending a tenth of a second under max acceleration, and it's spending half a second to almost a second at a reduced amount of acceleration. So that's what I mean when I say that these rocket engines burn very quickly. Like, we're talking total burn times of a second or less. Just, or I mean, you're welcome for the impressions of rocket motors. But that would be sort of that's what we're talking about. We're talking about like these motors burn very quickly. And that's just because, there's they use gunpowder and they're pretty small. So it's a highly reactive chemical reaction, and not a lot of it in there. So it just does its thing and then it's done. So anyway, that's that. What we're going to do is we're going to spend time basically creating this rocket design from scratch, so you guys can get a feel for how to create a rocket design from scratch in OpenRocket. So I'm going to go ahead and open up a new design. This is what I'm looking at here. I really didn't need to open up a new design because there's already one back here, but we'll just pretend that that never happened. So we got our rocket design, we got our motors and configuration, and we got our flight simulations. We already know all this stuff. We're going to get started by adding a nose cone. Boop. And this is the kind of dialog box that you get when you add a new component, because it's entirely possible to customize a lot of this stuff in order to get a whole range of options insofar as designing a rocket is concerned. You can have a big multi-stage monstrosity rocket. You could have a little tiny sort of goes up 30 feet in the air rocket, whatever. The rocket that you build in OpenRocket, the rocket that you build in real life, chances are it can be represented in OpenRocket and modeled and simulated and everything like that to a reasonable degree. So let's go ahead and spend some time taking a look at the options that we have here for a nose cone, because those are good to know. So we got nose cone shape. Nose cone shape is, as one might have guessed, the shape of the nose cone. We're going to stick to the option that comes up by default, which is, I believe, pronounced ogive or ogive. Ogive? I believe it's ogive. I think. Anyway, it's a conical nose cone with a curve to it, because as you can see, a straight conical one, I mean, it looks like a cone, but an ogive is a cone but with a flare to it, and it's just a decently popular profile for a nose cone. So we got shape parameter here. This adjusts the shape of the nose cone. As you can see, we can actually turn it into a cone essentially by reducing its shape parameter all the way to 0, but we're going to keep it at 1. And you can also see that the center of pressure, and to a lesser extent the center of gravity, or the center of mass, are moving as I change the shape parameter, because it tries to, to calculate this stuff in real time. So we're going to keep it at 1. We got our, our center of pressure here at the front, and our center of gravity here in the back. Not ideal, but we got to add the rest of the rocket first before we really start freaking out about that. And let's adjust our nose cone length. So I believe, if I remember correctly, yeah, I do remember correctly. Okay, so our nose cone length is going to be 10 centimeters. So we're going to make it a little bit stumpier, and if I just hit enter, I should see it update in real time. And base diameter, I believe, is going to be 2.5. Yes, 2.5. Whoops. 2.5. And hit enter. Boom. And so it's also going to be thinner. So essentially, it's actually going to be less stumpy than our original nose cone. It's just going to be a lot smaller. So we got our nose cone length of 10 centimeters and our base diameter of 2.5. The wall thickness is going to be 0.2 centimeters, I believe. Yeah, 0.2. What that basically refers to is the inside of this nose cone will be hollow, and we're interested in the thickness of the wall that makes up the structure of the nose cone. Now, adjusting that wall thickness will also adjust the center of gravity, because naturally, as you add more material to it, you're going to make the nose cone heavier, and it's going to be heavier in the back disproportionately because there's this big old area up here, and as you get it thicker, you're going to start having, more material in the back, which means that the center of gravity is going to move back more as you fill it in more. You could also fill it in entirely, but we're not going to do that, so we're going to have our wall thickness be 0.2. Nope, whoops, that's way too small, 0.2. Perfect. And we're going to change the component material to polystyrene, basically, yeah, type of plastic. So it's going to be a polystyrene nose cone. Now we're almost done. We've gotten the general profile of the nose cone. However, what we're going to do is we're going to add basically a stopper or a cork on the back, referred to as a shoulder, so that we can actually, attach it to the body. We can have it stick inside of the rocket body. So we're going to go to shoulder, and let's adjust these parameters here. So the diameter is going to be 2.3 centimeters. Nothing's changed so far, right? Well, hold on, let me drag the slider. So you can see we've got a sort of just another attachment on the nose cone starting to come out. The length is going to be 2 centimeters, and the thickness is going to be 0.2. There, making the thickness, increasing the thickness also move back the center of gravity, as you can see. And if we check end capped, you can see that it moves back a little bit further. Basically, it means that this area right here is going to be filled in. The very back of it is going to be solid, so it's not going to be hollow and see-through. Actually, I'll just go ahead and show you. So if we look at there, as you can see, this shoulder is hollow. If we click end capped, boom, filled in. And that's just to increase stability and stuff like that. So that's good. This is going to be our nose cone. Now let's go ahead and mess around with the appearance so that we can make it, whatever color we want, and, as shiny or unshiny as we want for our 3D finished view. And not really anything has changed because, I mean, it was by default white, but you can play around with that stuff and color it to your heart's content. Let me go back to the side view. So now we've got our nose cone. This is going to be our main aerodynamic component in a rocket. Duh. Let's go ahead and attach a body to it. I'm going to click on nose cone once, and I'm going to click on body tube. And boom, we get a body tube that appears behind it. I don't understand why it needs to be at 50% here, but anyway. So here we go with the body tube. We can change the body tube length. In this case, we want it to be 30 centimeters. We can change the outer diameter of the body, the inner diameter of the body, and the wall thickness of the body. Now that is to say, we can change, let me zoom way, way, way in. Hold on. Boop, 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 boop. Still just a line. So if we're looking at, this from the side, like this is our body tube, we can change the diameter measuring from inside to inside, or the diameter measuring from outside to outside, or the thickness of the wall. Now we can change any two of these. The third one is going to change on its own, because at some point you can't really fight against the laws of physics. So like if we're, messing around with our measurements, and we say that the wall thickness is going to be, this thick, and we say that the outer diameter is going to be this big, the inner diameter has to be a specific amount. It has to be, because if our wall thickness is 0.2 centimeters, like in this example here, if it's 0.2 centimeters and our outer diameter is 2.5, our inner diameter has to be 2.1. Otherwise, it makes no physical sense, because then our outer wall will be either embedded inside of our inner wall or floating off in space over here, detached from the actual body tube, and that just doesn't make any sense, and it kind of makes my brain hurt trying to think about it. So we can manipulate any two of these three, and then the third one will automatically adjust itself, and that's just kind of how it goes. So if we change wall thickness to 0.1, because we would like our outer diameter to be 2.5, if we change our wall thickness to 0.1, our inner diameter automatically adjusts to 2.3 centimeters. We'll go back to side view. We'll go back to fits. And now we're in business there. As you can see here under motor, we can say that this component is a motor mount. If we were so inclined, we're not going to do that yet because we're not actually going to mount our motor inside of the body tube itself. We're actually going to have a secondary thing inside of the body tube that we're going to mount the motor inside of. So we're going to keep that unchecked. And then you got this override over here. This is interesting. So based on the material that the part is made out of and its dimensions, OpenRocket does its best to try and guess at what the weight of that particular component is going to be. So like based on the fact that this is a 30 centimeter long, 2.5 centimeter thick body tube with a wall thickness of 0.1 centimeters. So based on that fact, plus the fact that it's 0.68 grams per centimeter cubed, it's like, okay, so your body tube is going to weigh this much. And it gets a pretty decent idea of that. But like, let's say, I don't know, you are using a material that's not listed here, or you're painting with very heavy paint that's not listed here. It's not even gonna, anyway. You're using some very heavy paint, like paint that actually has enough weight to affect the flight of your rocket, which I don't even know about what kind of paint you'd be working with there. But anyway, or maybe you throw a weight into your body tube in order to stabilize your rocket a little bit more. Well, under override, you can override those values. You can say, okay, so in reality, I know what my body tube is supposed to weigh, but in reality, it actually weighs this much. It actually weighs 830 grams. And the center of gravity should actually be right here, because the distribution of the weight on this body tube means that the center of gravity should be right about there. We're going to uncheck those because they don't. We're going with the regular values, but that's great if you have something that cannot be explicitly modeled and calculated automatically by OpenRocket. Like if you know these things, you go like, I know how much this body tube is supposed to weigh. Then you can go. Then you can say, okay, hey, so OpenRocket, my body tube actually weighs this much, and it will try and adjust itself in order to make up for that. Now, of course, you can comment on stuff like that, so you can be like, I painted my rocket with unobtainium. So now it weighs twice as much. So then when you look at it later, you're like, why did I make it so heavy? Well, then you can check the comments and you can be like, oh, okay, that makes sense now. And then, of course, we're back to good old appearance. Let me go ahead and create a nice blue color, a nice matte blue color. Go down to 3D finished. Look at that. Look at that pretty blue color. Anyway, so that's our body tube. Go back to the side view and not misclick all the freaking time. So now we're looking at body tube and a nose cone. Pretty straightforward, right? Let's go ahead and let's add some fins to this. Now you'll notice I clicked on body tube, so now it's highlighted in this brighter blue. That's because I need to have the body tube selected in order to add any of these other parts. So we're going to go ahead and add some fins to our body tube. Select it once, or click it once so it's selected. Click on trapezoidal. And this is what you're looking at. A lot of stuff. In fact, we can pretty safely ignore all the stuff on the left side for now. But I'll tell you what it does anyway, just so you kind of have an idea of what it does later on. So the number of fins, obviously pretty self-explanatory. We adjust the number of fins that exist on the rocket. We can give it a million fins, and by a million I mean 8. Excuse me. Just had a coughing fit. Anyway, we can adjust the number of fins that exist on the rocket, and woo, it's a very stable rocket, very, very stable rocket. But we're not going to do that. We're going to have 3 fins. We can adjust the fin rotation, which is basically the orientation of the fins on the rocket. So you see if I turn this, it actually is, the rocket itself is not spinning, but the fins on the rocket are. So we're changing the default positioning of the fins. This doesn't matter. That doesn't matter because we're only going to have one set of fins on this rocket. However, if you're working on a rocket that has like a few different sets of fins, you can have one set be rotated, offset from another set, so that you can make sure that there's always that you're not trying to make like the lower fins less effective or something like that, or you can have them on the same orientation so that you're not increasing the amount of drag on the rocket, whatever the case may be. You have that freedom in order to rotate the fins. The fin canting, see if I turn this all the way up to 15, you can see that there's there's almost sort of a rifling effect that happens here. So we can make it so that our rocket will spin as it's ascending. It will just be spinning, which can be good for stability, but it's certainly going to have a lot of drag. It's going to have a lot of drag, and your rocket will certainly not be able to go as high. Root chord is basically the length of the fin on the back ends, and then the tip chord is the length of the fin on the far end. If I say back end, I mean the end closest to the rocket body. Height is how long the fin is. Sweep length and sweep angle are related. So the sweep is this bit right here. Let me draw it on this one. It's that leading slant. As we make the sweep length longer, we actually change the sweep angle. So we can change how the rocket fins look that way and how they affect things. What we're interested in is the fin cross section. So the fin cross section, let's go ahead and go over to the 3D finished view. The fin cross section is this business right here. It's the front. So what I'm going to do is I'm going to change it from a square cross-section to a rounded cross-section, and you're not really going to see it change a whole lot, in fact, at all. But we are going to change the thickness down to 0.2 centimeters, which you're going to see the fin get thinner. Boop. There you go. Component material cardboard. I believe, actually, we can probably do... Oh, well, I guess not. Anyway, let's go ahead and do that anyway. So we'll make it out of balsa. Oh, wow. Maybe that's why they kept the cardboard, the center of gravity. So we'll have birch, which is a similar weight, but it's still a, a light wood. Light and sturdy wood. Fin tabs allow us to adjust the tabs that attach the fin to the body tube. Override, we already talked about that. Mass and center of gravity. Appearance, well, we've talked about this too. We'll go ahead and make white fins with a very shiny shine. And we'll click close, and this is what we've got so far. It's a very pretty looking rocket. It would look quite nice flying up into the air. Anyway, go back to side view, make sure it fits. It does fit, perfect. Now we are going to add an inner tube, right? We were going to add an inner tube. Yeah, inner tube. All right, cool. We're going to add an inner tube to our body tube. Click. So I had my body tube selected and I clicked inner tube in order to add it. So this is our inner tube. As you can see, it's got a nice sort of purplish kind of color in order to distinguish it from the body tube. We've got an outer diameter, an inner diameter, a wall thickness, and a length, as well as there's this position relative to the bottom of the parent component plus blah, blah, blah. This allows us to offset the inner tube from the outer tube, and you'll see what I mean in a second. So if we make the length of the inner tube, we'll add 0.5 centimeter to it, so it's 7.5. As you can see, it adjusted it up here in the front. It made the front longer. However, what we're going to do is we're going to position it relative to the bottom of the parent component. We're going to add 0.5 centimeters. I believe these are the dimensions we want. Yeah. So now you can see that it's sticking out of the back a little bit. So now we got 7 centimeters on the inside, just like we had before, but we have an extra 0.5 centimeters of wiggle room out of the back of the rocket, and that's where we're going to actually mount the motor so that it doesn't, burn the back of the rocket and all that, fun stuff. We're going to try and avoid that as neato as it can be. So yeah. How do we know we're going to mount the motor there? Well, we can just click on this motor tab. There you go. Checkbox. This component is a motor mount. Click. And we're actually going to add a motor overhang as well of 0.3. 003. There we go. You won't see it update here. You in fact will not see it until we actually add a motor to the rocket. But we've got the inner tube hanging out about 0.5 centimeter from the back of the rocket, and then we're going to have the motor hanging out 0.3 centimeter from the back of the motor mount. So there's kind of just going to be like sequential sort of overhangs in order to create the ideal system. Just to make sure that we're not damaging the fins on the rocket or anything like that with the exhaust from the motor. So let's click Close. So now we've got our body tube, our trapezoidal fin set, our nose cone, and our inner tube. Exciting, right? Super exciting. Woo. I mean, that sounded sarcastic of me, but I just meant like, you know, look at that inner tube. Look at how it's just sort of floating out there and nothing. Let me go back to the side view, and let me go up to motors and configuration, because here's the thing. We've got our center of gravity here. We got our center of propulsion here, or center of pressure, excuse me. And they're just way far apart. In fact, our stability is 4.24 calibers. It's almost 4.25 calibers, which is way too high. But that's because we don't have the innards of the rocket done, including the engine, the super heavy, relatively speaking, engine. So let's fix that. I'm going to click up here on Motors on Configuration. We've got this motor mounts thing over here. Body tube has an unchecked box, and inner tube has a checked box. This is where you can very quickly set up additional motor mounts if you forgot to do them there. We'll keep this as it is though, because our body tube is not actually going to be a motor mount, but our inner tube is. So that's perfect. So we'll go ahead and click on New Configuration, and what it's going to do is it's just going to automatically set up a blank configuration for us. Configuration, no motors, inner tube, none, default, automatic. So let's go ahead and double click here in order to bring up a dialog box, which is it's got a lot of stuff going on it. Select all. There we go. A lot of stuff going on it. A lot of engines. And these are all just known manufacturers and engine classes and things like that that you could then put into your model rocket. Now here's the thing. This has got a lot of information on it. It can go all the way from 1/2 and 1/4 A, which, let's see here. So let's say, you know, well, they're actually going to be 1/2 and 1/4 of the power of a Class A rocket, respectively. But these go all the way up to O. Class O rockets are listed in here as well. So let's just hit OK and see what happens. Now watch this. This is a Class O motor, this gray area right here. This is how big it is relative to the rocket. The rocket is smaller than a Class O engine. Think about how big the rocket that engine is slotted into needs to be. That's ridiculous. This thing is 803 millimeters in length. It is almost an entire meter. It is almost 3.3 feet long. In fact, this one's almost 2 meters long. This motor is as big as some people. You have a Class M engine? Awesome. Yeah. But yeah, there are Class O engines out there which are as big as people. They're as tall as people are. That's crazy. Anyway, that's neither here nor there, because we can't exactly put a Class O engine into this rocket. As you can see, the rocket is not big enough to really be able to. Yeah. So let's go ahead. As you can see here, putting this Class O engine just kind of assumes that it'll work. So it has an apogee of 53,000 meters and a max velocity of Mach 3 and a max acceleration of 417 meters a second. because you know, it just kind of like it's like, yeah, okay, this works, sure, yeah, this will go to the moon, 154,000 meters. Good Lord, that that's 154 kilometers. That's like the edge of space. Anyway, this will not work because that engine is far too big. Let's go down to more reasonable sizes, shall we? Sorry to disappoint, by the way. Um, but there's so many options, you know, which one do we pick? Well, let's go ahead and narrow our options down. We can filter our motors by manufacturer, we can filter it by impulse, we can filter it by motor size. We're definitely going to have to do that, but we're going to filter it by impulse and manufacturer. If we clear all of them but just select Estes, we've got a few options here. The 1/2 A3T, the 1/4 A3T, the A10T, A3T, half A6, A8, B6, and B4. We're actually interested in the A8. If I click on it, as you can see, select thrust curve A8 is grayed out. However, I can set the ejection delay charge, which I'm going to have be a 3. But I want to show you this details over here. So show details gives us basically the stats for the motor. It's got a total impulse of 2.32 newtons. Okay, not bad. It's got an average thrust of 3.48 newtons. It's got a max thrust of 9.73 newtons. And this probably means nothing to you. Like, it's just like, oh, it's got a max thrust of 9.73 newtons. Wow, talk about a powerhouse. But you know, it's generally speaking, that higher numbers are stronger. So you can sort of get an idea from that. Like if we look at A8 and then B6, we can say, oh, the max thrust is 12 newtons as opposed to 9 newtons. And its average thrust is 5 newtons as opposed to 3 newtons. So we know that the B6 engine is going to be stronger. We can also see that the burn time of this A8 is 0.663 seconds versus 0.826 seconds of this B, or 0.996. And it still get, like a stronger thrust. But anyway, we can look at this thrust curve here. We can see the amount of thrust that the motor puts out over time. So as we can see, the max thrust is 9.73 newtons. We almost hit 10 newtons, about 2.3 or 0.23 seconds in, about, roughly. And as you can see, the thrust stops abruptly right at about 0.65. As you can see, burn time 0.663. So the thrust drops off pretty abruptly. The average thrust, 3.48 newtons. You can see that it actually hangs out for most of its time a little bit below 3 newtons, about 2.5 newtons. But the fact that it hits almost 10 for a second there means that the average is thrown way off. And total impulse, that's about this area right here, the 2.3 and all that stuff. So this is a thrust curve. It gives us an idea of the amount of thrust that an engine will put out over time. Good to know. Whoops, did not mean to do that. I just wanted to show the thrust curve off for something like a B engine. 12 newtons. 12.1 newtons. As you can see, the total impulse is 4.33, and we're hanging out right at about 4.33-ish. Average thrust 5.23. Again, average is a little bit below that, but then the peak throws off the average. Burn time 0.826 seconds. We really start to lose thrust around that time. So on and so forth. You get the idea. We can spend some time reading this or whatever, but you get the idea that it gives us an idea of sort of how these engines will perform relative to one another. Motors will perform relative to one another. So I'm going to select the Estes A8. I'm going to set the ejection charge delay to 3. I'm going to hit OK, and we get our rocket stats. The apogee is 73.2 meters. Not very high. Certainly not relative to our O-class engine slotted into this thing somehow. Our max velocity is 37.4 meters a second, so Mach 1/10 of Mach 1. 1/10 the speed of sound. The max acceleration is 171 meters a second squared. So we burn for significantly less than a full second. We're under max acceleration for significantly less than a full second. And that shows in our stats here. The burn time in total is only 2/3 of a second. And max thrust is where it's under max acceleration. So that's what for, I mean, let's say these two data points here. That's about a 20th of a second. So yeah, it does not spend very long at max acceleration. All right. So we slotted that in there. We've got a very bare bones starter rocket. We don't have some things that are missing that we have no means to recover it. We have no means to stabilize it on the launch pad, stuff like that. So we're actually going to have to spend Wednesday working on that because we're just about out of time today. And we'll also probably, fine-tune the motor configuration and stuff like that so we have a better rocket and show off the flight simulations and everything. But as it stands right now, I'm going to go ahead and I'm just going to skip the poll questions since we ran till just about 5 minutes before and leave it open to question and answer time. And if you have any, you're more than welcome. Otherwise, you're more than welcome to head out. Have a wonderful couple of days, and we'll see you on Wednesday.